So welcome back. This is our third video about graph decomposition, and now we're going to discuss how we can transform a joint tree into elimination order. But let's first recap what is a joint tree, the definition, and from there we're going to discuss how to transform the joint tree into elimination order. So the joint tree for a network G doesn't need just to be for a DAG, but also to a network. So it can be a Bayesian or a Markov network. Is a pair TC, where T is a tree. So the structure must be a tree, no loops here. And C is a function that maps each node I in the tree into a label Ci, call it the cluster. And the joint tree must satisfy the following properties. The cluster Ci is a set of nodes from the graph. Each factor in G must appear in some cluster Ci, and if a variable appears in two clusters Ci and Cj, it must also appear in every cluster Ck on the path connecting I to J in the joint tree. It's known as a joint tree property or the running intersection property. Okay, so again, we have a Bayesian network here. We have a joint tree on the right side. So this is the Bayesian network. This is a joint tree. And we can think about those properties, right? So first it must be a tree. We have those clusters. Each cluster Ci is a set of nodes from G. So like F. DG, F is occurring here, D is occurring here, and G is occurring here, and each factor in G must appear in some cluster Ci. That is a little bit more complicated to check, but we can think about, for instance, we have a factor here that mentions F, G, and D, so we can place this factor here. And we must find one node for each factor that we have in the Bayesian or in the Markov network. And maybe the most strange thing here is this joint tree property that says that if a variable occurs in two clusters, it must occur also in the path. So, for instance, if you look at A here, A is happening here in node 5. It's also happening here in node 2, so it must occur in nodes 3 and 4, and that is true here. So we can see A in the nodes and also in the separators. So a relevant question is, why do we need this joint tree or running intersection property? And the reason is actually very simple. We cannot eliminate that variable A. If we do that, we may have other factors that mention A that they're not part of the elimination process, and that's going to be wrong, right? So we know that in order to eliminate a variable, we need to multiply first all the factors that mention that variable. So what's going on here is that if you think about A, we can have a factor that mentions A here, one factor that mentions A here, another that mentions A here, and another that mentions A here. It can be true or not, we don't know. We don't know how we split the factors according to the clusters, but it is possible. So if we say that we're going to take A out of here, it's also true that we need to remove it from the separator, right? And it means that when we send the message here, the message will sum over A and eliminate the variable A because it's not part of the separator. And in this case, if we have a factor that mentions A in 3, first, we could not put the factor that mentions A because we removed it here, but we could have a factor that mentions A, for instance, here in the node 4 or in the node 2 here. So it is the case, it's going to be wrong because we eliminated A here without multiplying all the factors that mention A. So the running intersection property or the joint tree property is a key property to make the inference in the correct way. So we must have that property. It must be valid. Okay, we also have the concept of separator that basically tells us what are the variables that you need to continue it, right? So we cannot eliminate when we send a message from one node to the other. We need to have those messages, those variables in the message. So the variables that appear in the separator must be in the message. So it says that the separator of edge ij in an elimination node in a join tree, I'm going to fix that later, is a set of variables defined as the intersection between the variables that have one node and the other node in the opposite sides of the edge. So in this case here, AD is the intersection between ADF and ABD. So we have A and D occurring in both sides of the node, so that is the separator. These are the variables that we cannot eliminate, right? So don't forget about it. We cannot eliminate those variables because they are occurring in the other side, so we can only eliminate the variables A and D after we multiply the other factors that are mentioned in those variables. They have two definitions here. Width of the joint tree defined as the size of the largest cluster minus 1. Great. In this case, this joint tree here has width equal to, because the largest cluster has size 3. The joint tree is also called the junction tree or the cluster tree. Okay. Let's take a look on the next slide. Okay, so these are transformations over joint trees, and this is new. We have never seen this before, so that's an end of our recap, and let's take a look on this. So we have these 4 operations here that we can do over joint trees, and we're going to preserve all the 3 properties of the joint trees. So we can do these operations and we will still have the 3 properties, including the joint tree property. That's very important. So we can add a variable, we can merge clusters, we can add a cluster, or we can remove a cluster. So let's take a look on the first one. We can add a variable. We can add a variable x to a cluster Ci if Ci has a neighbor Cj that contains x. So, for instance, let's suppose that we have this Bayesian network here. This is a joint tree for this Bayesian network, and I want to manipulate this. And for instance, I want to take this variable d here and include this variable here. So I'm going to have this cluster here over C, E, and D. I can do this because this cluster has a neighbor that has the variable d. Originally, we have CE and BCD, so this separator here was over the variable C. But if I move the variable d for this cluster here, I will need to add the variable d to the separator too. So I can add the variable. What's going on here? I am including one more variable in this cluster. It's going to be good because I can answer now queries that mention C, E, and D, but on the other side, I need more space to store a larger factor. Okay, we can also merge clusters. Let's just erase this, otherwise it's going to be too messy. Okay, so we can merge 2 neighboring clusters, Ci and Cj, into a single cluster, Ck, that is the union of Ci and Cj, where Ck inherits the neighbors of Ci and Cj. Okay, so for instance, merging clusters. So let's suppose that we have this joint tree here, and we want to merge these 2 clusters together. So can we do that? We can. We can. And in this case, the new cluster that's going to replace these 2, we have the union of both clusters. So the variables in both clusters. So in this case, we have the union of ABC with AB. That's just ABC. So we can replace these 2 guys and have a merge and have this as a new cluster. And that's good, right? So we can do this, and in this case, it did not grow the clusters, but with it, we take 2 clusters that have different variables that can happen, right? So for instance, we could decide that I'm going to merge these 2 clusters here. Okay, so I'm going to be the merge of BCD union with CE. So the result is going to be B, C, D, and E. So it's going to be a larger cluster. That's fine. So we can merge this, and in this case, we're going to eliminate the separator here and merge the clusters. Again, when we do this, there are two different situations. The first one is like this that we did first. We merged it because we have this smaller cluster that was a subset of this larger cluster here. It would be good to eliminate this. We are saving a little bit of space, and we can still answer the same queries that we had before, right? So we are not creating any cluster that's larger than we had before. Or we can also merge two clusters that will result in a larger cluster as we did here. That's also good. In this case, what we are gaining is the fact that we can now answer queries over this larger cluster that involves B, C, D, and E, and we could not do that with the two separated clusters. All right, let me just erase this again. And we can add a cluster. So we can add a new cluster CJ and make it a neighbor of an existing cluster CI if CJ is a subset of CI. So exactly what is going on here, right? So we decide to add a cluster. So we can add a cluster here. And here we can put A, we could put B, we could put C, we can put AB, we can put AC, BC, or whatever, any combination that we want. As far as whatever we got here is a subset of what we have here. In this case, we need to set the separator correctly. In this case, it's going to be AB, and we created this guy here. All right, the last operation is to remove a cluster. So we can remove cluster CJ if it has a single neighbor CI and CJ is a subset of CI. So it's also exactly what we have here. So this cluster, this guy here, has just one neighbor, and the variables that I have here constitute a subset of the variables that we have here. So we can eliminate this guy here, and actually we go from the left joint tree, the right joint tree, the right joint tree to the left joint tree. So all those operations are valid. They will change a joint tree, but they will preserve the properties that we have in the joint tree. So good, but why we are talking about those operations, right? So what are the uses for those operations? So actually, they are quite useful in practice. So we have listed here a few ways that we can use those operations. So first, the addition operation, the addition of a variable D allows the joint tree to compute a marginal over variables C, D, and E. So when we add a variable D here, right? So now we have a larger clusters over variables D, C, D, and E. And we didn't have this before, so we were not able before to answer queries over this marginal here. So we are gaining the ability to answer queries over this marginal C, D, and E. So this marginal will not be computed if the algorithm was applied to the left joint tree. That's good. Merging two clusters eliminated the separator connecting them. And if we look at the architectures like Shenoy-Schafter or Huygens, those algorithms, they create factors over the separator. So this transformation can be used to reduce space requirements. So when we merge clusters like we did here, we are eliminating the separator here. In this case, we are saving space. We are saving space for this separator. In the case of the Huygens architecture, we are also saving the space that we use to store the factor in the cluster. So we can gain a little bit of space when we do that. On the other hand, we will increase the running time when we merge clusters and we create larger clusters, right? So in this case here that we are merging these two clusters, but the resulting cluster has the same size of the original one, we are just saving space. But in case that we merge two clusters and create another cluster that is larger than the previous ones, so that will be compromised in terms of efficiency. And just remember that the algorithm is exponential in the cluster size, so as we include more variables into the clusters, we make the algorithm slower. Great, some final touch here is that these transformations can be a base for some time and space trade-off. So sometimes we have a little bit more space, so we can create a larger cluster. Sometimes we need to save space, so we need to keep the cluster small. So we have those operations that we can transform the join tree and tune the join tree to the requirements that we need. Yeah, if we need to answer queries over a larger set of variables, so we can include those variables into some of the cluster and be able to answer the queries at the same time that we need more space in order to store the cluster in memory. Okay, so let's take a look at one first algorithm. This algorithm will convert a join tree into an elimination order. Later on, you're going to see the opposite algorithm that transforms elimination order into a join tree. So this algorithm has the following steps. So first, we start with an empty elimination order pi. So we're going to have an empty elimination order pi. While the tree is not empty, so I'm going to decompose the tree, and this tree is the join tree. So I'm going to decompose this join tree and node by node until we have an empty join tree. So we're going to remove a node I from the tree, from the join tree, that has a single neighbor j. All right, so if we look at this join tree, we have actually 4 nodes that we can start. We can start with this node here. It has only one neighbor, this one, and this one. So the algorithm is leaving this open to us. We can choose any of them. Let's suppose that we choose this one, and I'm going to eliminate this fdg node. We append the variables ci, so the variables are in ci, but they are not into the separator to pi. So pi will have first a variable here. Let's take a look carefully, because we have f, d, and g, and we have a separator df. So the first variable that we can eliminate is g, right? It should be very clear, because that is the only variable that we are eliminating when we do this pass over here. So when we send the message from this node to the node on the bottom here, so when I send this message here, we are eliminating the variable g, right? Okay, so we go to the while again, and we don't have an empty tree, so let's continue doing that. So we need to choose another node. Let's suppose that we choose this node here, so we can eliminate this node. It also has a single neighbor, and we have ACE, and AE is the separator. So we can put the C here. That is the only node that we can eliminate. We can continue with that. Let's suppose that we go to this node here, ABD, and we have the separator AD. So the node that we're going to eliminate is B. And we can go to this one, E, F, and G, and we can eliminate that. We have EF, so in this case, it's going to be age, EF and age. All right, so we have these two nodes here. Let's suppose that we decided to eliminate this one here. So we have ADF, and the separator is A and F, so we can eliminate D. And now we have this node here that mentions A, E, and F. And so we can put these 3 variables here, and we can have any order between them. That represents that way, A, E, and F. So we can do any permutation here, and for these final 3 variables. So this is basically a process of simulating the inference in the joint trees, right? So we are doing the inference that it is supposed to do in the joint tree when we are sending the messages. And we are just using the information that we have in the joint tree to figure out which are the variables that are going to be eliminated. There are some decisions here that are open, but those open decisions will not interfere in the performance. What's happening here is that this elimination order that we have here has the same width as this joint tree. So in terms of the width of this guy here is equal to the width of this guy here. So this is a little bit more organized walk through this example, and not sure if the elimination of the variables is in exactly the same order. The elimination of the nodes is exactly in the same order, but if you choose a different order, it will give us a different elimination order pi here, but it's guaranteed that this older elimination order will also have the same width as the joint tree. So great, let's see what we have here. So this algorithm simulates the process of factor elimination. That's true. It runs in polynomial time. That's also true. So we take each node at a time and eliminate that. So we're just sort of simulating the process of eliminating the variable. So we are not doing any joins or any divisions or any summations. So the expensive part of the computation is not done here. So it's just sort of a simulation. So it will take a time that's proportional to the number of nodes that we have here. It provides an elimination order of no greater width than the joint tree width. All right, so the algorithm leaves a few choice undetermined, choosing the node I to remove the next from the joint tree, and choosing the order in which the variables that we are taking here. In this case, it happened that each node that we eliminated had just one variable, right? So just this final one here had the three variables that could come out in different ways, in different orders. But sometimes we eliminate a node like this one, and the separator, we have three variables here, and the separator has just one variable here. So we have two variables, and we need to decide if it's going to be, what's going to be the order between these two variables. It doesn't matter. None of those choices matter to the guarantees provided by the algorithm. Okay, that's good. All right, so that's good for this video. Let's make a pause because we need to discuss the order operation that we're going to take elimination order and convert into a joint tree. But we're going to do that in the next video. So see you soon.